For decades, solar physicists have wrestled with a stubborn question. Why does the sun's plasma cool so quickly after a flare? Classical models predicted that the superheated gas in the corona, plasma reaching over 1,000,000 degrees, should take hours or even days to cool. Yet telescopes showed something else entirely. Within minutes, that same plasma collapses into brilliant streams of glowing rain, cascading back toward the sun's surface. It was a paradox, until now. A new study has finally uncovered what was missing. The key wasn't hidden in energy or magnetism, but in chemistry. The secret behind solar rain. Our star, the sun, is a place of unimaginable violence and breathtaking beauty. Its outer atmosphere, a superheated plasma called the corona, stretches millions of kilometers into space. Here, titanic explosions, known as solar flares, unleash the energy of 1,000,000,000 hydrogen bombs. But after the fireworks fade, something extraordinary happens. Cooler plasma begins to fall back through the corona, forming shimmering curtains of what scientists poetically call coronal rain. For decades, we've seen it through the eyes of NASA's Solar Dynamics Observatory and other powerful telescopes. But the mystery wasn't what we saw. It was how fast it happened. Existing models predicted this cooling process should take hours, yet observations showed it happening in mere minutes. The physics just didn't add up. Researchers Luke Bonowitz and Jeffrey Reep suspected that a long-held assumption had been holding solar physics back. The idea that the sun's coronal composition stays constant during these violent flare events. Their new, more complex simulations proved that's not true at all. During flares, heavier elements like iron, which are normally settled lower down, are dredged up and surge into the corona through powerful plasma flows. And that changes everything. Iron and other elements that are easily ionized are incredibly efficient at radiating energy away. This is known as radiative cooling. When their concentrations spike, the plasma suddenly has a new, super-effective way to cool down. It's like opening a massive thermal vent in a pressurized container. The temperature plummets, triggering a runaway condensation effect. The result? The rapid, catastrophic condensation that creates the beautiful, fast-forming spectacle of solar rain. Once this variable chemistry was added to the models, the numbers finally matched reality. The cooling timeline snapped into focus. Minutes, not hours. This breakthrough doesn't just solve the mystery of coronal rain. It provides a crucial new framework for understanding energy transport in the sun's atmosphere, a key piece of the puzzle for predicting space weather that can affect us here on Earth. Observation and theory finally aligned, opening a new chapter in our understanding of the sun, a new era of flare physics. This isn't a minor fix, it's a fundamental paradigm shift in our understanding of the sun. For decades, our models of solar flares were built on a crucial yet flawed assumption. They treated the chemical composition of the sun's superheated outer atmosphere, the corona, as static and unchanging. This simplification was a necessary starting point, but it masked a deeper, more complex reality. Now we know the corona is profoundly dynamic. The sun's own chemistry changes in real time, driven by the very flares we seek to understand. This discovery reshapes how we interpret the flow of solar energy. It means that the cooling patterns we observe aren't just the quiet aftermath of a flare. They're a direct reflection of how elements move and transform within it. In solar physics, cooling is the shadow of heating. We can't directly watch the moment of energy release, But by studying how the plasma cools, a process called radiative cooling, we can decode the hidden physics. Instruments aboard spacecraft, like the Solar Dynamics Observatory, allow us to read the spectral fingerprints of different elements, revealing their changing abundance as the plasma cools. This new framework finally connects three phenomena that once seemed separate. First, the FIP effect, where elements that are easy to ionize, like iron, become mysteriously enriched in the corona. Second, flare-driven flows, where these powerful eruptions act like elevators, lifting that enriched plasma high into the solar atmosphere. And third, runaway condensation. The high concentration of heavy elements causes the plasma to radiate energy and cool much faster. It's like a humid summer day when a cool breeze suddenly causes water vapor to condense into rain. Here, the enriched plasma rapidly collapses into the beautiful fiery spectacle of coronal rain. The FIP effect loads the gun, the flare pulls the trigger, and runaway condensation is the result. Everything fits. Why? It matters. This discovery does far more than just explain the beautiful phenomenon of coronal rain. For decades, our models of the Sun treated its atmosphere as a chemically static environment. But this new understanding forces a paradigm shift. It fundamentally rewrites how we model the Sun's behavior, with profound implications across solar physics. First, we must rethink coronal heating. Simulations of solar flares, loops, and magnetic reconnection events can no longer assume a fixed chemistry. They must now incorporate this dynamic composition, where the elements themselves influence the flow of energy. Second, this leads to better space weather forecasts. By understanding how flares cool more rapidly due to this elemental sorting, our models can more accurately predict the timing and intensity of coronal mass ejections. This is vital for protecting our satellites, power grids, and astronauts from dangerous solar storms. Third, it promises sharper spectral diagnostics. When we analyze the light from the Sun, we can now account for these real-time abundance variations. This will make the data gathered by solar missions far more precise, unlocking new layers of information from the spectra we observe. Fourth, there are stellar implications. Other stars show similar flare-driven activity, and this model could be a key to explaining their own atmospheric energy cycles and chemical compositions, extending this discovery across the cosmos. And fifth, it provides a new framework for next-generation observations. Missions like the Solar Orbiter and Parker Solar Probe are perfectly positioned to test these predictions, using their instruments to measure elemental changes in the solar wind as they happen. The message is simple but profound. The elemental composition of the Sun's atmosphere isn't just background noise. It is an active, dynamic ingredient shaping the story of our star, a story we are only just beginning to read correctly. A dynamic star. By embracing the Sun's changing chemistry, scientists have solved one of solar physics' oldest riddles: why the corona cools so fast after flares. It turns out the Sun is not just a roaring furnace of plasma. It's a living laboratory, constantly mixing, reacting, and reinventing itself. Even after centuries of study, it still finds ways to surprise us. The rain that falls on the Sun isn't just plasma cooling. It's the chemistry of a star revealed.